Hello, this is Jack Jackson. In this video, we're going to continue our work on looking at the chain rule. So we're going to use my GeoGebra activity that I showed you in the last couple of videos. But we want to be examining the derivative of e to the 1/4 x squared. Now suppose at this point we know that the derivative of e to the u is e to the u, and we know the derivative of 1/4 x squared is 1/2 x. But we don't know how necessarily to do a derivative like this one. Okay, so what we want to do is we want to do a substitution. If you let the u be 1/4 x squared, this becomes e to the u. So the outer function as a function of u is f of u is e to the u. The inner function then is g of x, which is 1/4 x squared. And that's our u. Okay? So let's take a look at the app and see what we can do with that. Now, I need to put the formulas in. So the outer function, the outermost structure is e to a power. In GeoGebra here, that's exp of the power, which is going to be u. So I need to write this function in terms of u. That should change this to an exponential graph over here on the right. And the inner function was, I think it was 1/4 times x squared. This is the same functions that we looked at earlier when we were talking about composition of functions. And so just to review, when you take an input here, you apply the function f, that gives you the purple length here. Take that over, make it a horizontal length over here, apply the function, I'm sorry, there's a function g was first. Apply that over here, we get the function f, it sends it up to here. That orange length comes back here to locate the function on the composition graph. So the original function is c of x that we want to find the derivative of. That's e to the power 1/4 x squared. Alright, so that's the composition. Now let's look at the tangent lines to see what's happening with the derivatives. So let's can experiment. So let's put this at, say, 2.5 for the input. And we can see the derivative as the slopes of the tangent lines. So when I click on the tangent line box, we see the tangent lines appear. And the slopes of those lines then are how much they go up or down, or in this case going up, when we go to the right one. So they're represented by these vertical vectors here. So the slope of this blue tangent line to the blue graph is g prime at whatever, in this case, whatever a is, at 2.5. And that's 1.25. That's this vertical change here when we go the right one. That's the slope of that tangent line at that particular point right there. G of a, comma g of a, 2.5, comma 1.56. And so that slope is 1.25. If we take the function f of u, that's e to the u. This is 1.56, comma 4.77 is this. And we know one interesting fact about the graph of e to the x, or e to the u here, is that the y value and the slope are the same. The slope of this tangent line here, this length here, 4.77, it turns out to be the same as this orange length here. And so anyway, that's the slope there. And it turns out if you multiply those two together, do you get this? That's what happened in the linear example last time. Check it out. Yeah, in fact, if you do take the 4.77 times the 1.25, you do get 5.96. There may be a little rounding off going here, but they should turn out to be the same. So that's the slope that we get here on the tangent line here. To work out the formula, here the details worked out. C prime of x is the derivative of f of g of x. That's f prime evaluated at g of x times g prime of x. Or in other words, that's f prime of u times g prime of x. Well, f prime of u is e to the u, and g prime of x is 1/2 x, but u is 1/4 x squared. I'm not going to write that in the front. And there's the formula for the derivative that we're looking for. And we see, of course, if we plug in the particular x value of 2.5, you're going to get this number down here. And we see that worked out with just the product of those two slopes. And so there's the chain rule in action. In the notes you will see here, there's the algebra worked out as well. And there's a screenshot of the picture we just looked at. Now let's actually do the actual proof. Okay, so we've seen a visual illustration of the chain rule. Now let's work out the actual algebraic proof to show that this works. So to start the proof, let's recall a couple of things. And when we're looking at difference quotients, then we always let the letter h represent delta x. So delta x and h are the same thing. So delta g then is the numerator of the difference quotient. That is g of x plus h minus g of x. That's the change in g. Now g of x plus h then is delta g plus g of x. Now g of x plus the amount of change in g gets you to the new value on g. So here we go through this. The derivative of f composed g of x is the derivative of f of g of x. Well, that's f composed g of x plus h minus f composed g of x. In other words, f of g of x plus h minus f of g of x. Divide that by delta x and let delta x go to 0. That's from the definition of the derivative. Now g of x plus h is g of x plus delta g. Okay. Now I'm going to multiply top and bottom of this fraction by delta g over delta g. And I'm going to sort of switch places with the delta x and delta g here, which is allowed. Now I want to think of this as two limits. The first one I'm going to think of as delta g goes to 0, because as delta x goes to 0, delta g goes to 0 as well. And the second one I'm going to think is delta x goes to 0. Now if both of these limits exist, then the overall limit exists up here. Now this limit, if you think about it, is just, it's f of g plus delta g minus f of g over delta g as delta g goes to 0. Well, that's just f prime of g, f prime of u, f prime of g, f prime of g of x. And this last one, that's another way of just writing the derivative of g with respect to x. And so we get the result that we want. So we've now proved what we set out to prove, the composition or substitution rule, or officially named the chain rule. The derivative of f composed g of x is the derivative of f of g of x. That's the derivative of f evaluated at g of x times g prime of x. Or, if you do it the way I like to think of it, if you substitute u in, that's the derivative of f of u. That's f prime of u times the derivative of u. Or, in Leibniz notation, df over dx is df over du times du over dx. We're going to put this to work in some contextual applications in the next video, and the one after that we'll do some formula computations.